Hello everybody, welcome to a video on section 2.1. This of course is not ideal, but as I explained in my email, we really can't lose a day of material due to the snow. The schedule is pretty tight before spring break. Also, I apologize for any crying or screaming that you hear in the background. I don't have an infant anymore, but my 3-year-old son certainly behaves like one sometimes, so I apologize for the background noise. Okay, so the point of section 2.1 is to solve first-order linear differential equations. I'll talk about the definition in a second. Let me just put the section in a bit of context. So recall the way the course works. We learn how to solve some DEs so that we can apply them to things like physics and ecology and whatever. Chapter 2 is sort of a little microcosm of that. So the way Chapter 2 works is for the first 3 sections of Chapter 2, we learn how to solve differential equations in no context. There's no physical context to these things. Then we spend 3 days applying them. Okay, so 3 days of just solving DEs, 3 days of applications. So this section fits into those first 3 days of just solving DEs. We'll get to the applications at the end of the chapter. So these equations are incredibly useful. So anyway, a first order linear DE is a DE that can be written like this. The derivative of y plus some independent variable stuff, doesn't matter, times y equals some other independent variable stuff. In the previous section, section 2.2, x was the independent variable all the time. In this section, t will be the independent variable all of the time. It's just for historical reasons, switching between x and t. So sorry if that's confusing, but in this section, there are no x's actually, only t's, for time, probably. But anyway, so a first order linear DE is just something that can be written as derivative of dependent plus any independent stuff you want times the dependent equals any independent stuff you want. So we're going to learn how to solve differential equations like this. The solution technique is known as integrating factors. And basically the way it works is just to sort of undo a product rule. So you sort of notice that a product rule happened, and then you undo it. Okay, so the technique of integrating factors is weird at first. It takes some getting used to. So rather than describe it abstractly and in general, I'm just going to show you how it works in an example. So let's think about this differential equation here. dy dt minus 2y equals 4 minus t. Notice that is in the form I have written here. It's already in that form. Notice there's a 1 on the dy dt, right? There's a 1 coefficient on the dy dt. You have a function of t there, just a constant function. So like p of t equals negative 2. I guess there's a negative there. And on the other side, g of t is 4 minus t. Okay, so the way all of these problems work is that you start by multiplying both sides of the equation by a function mu of t. Now, once we've done this once, okay, when we move on to our second example, we'll actually know precisely what mu of t is. But for now, we don't know it because I haven't explained the method to you. So you slap a mu of t everywhere in this differential equation. And your first reaction is probably confusion, like why are we doing this? Among other things, this differential equation looks way more complicated than the original one, so not clear why you'd be doing this. Also, of course, eventually we'll have to figure out what this mu is and what it's doing. But for now, I'm asking you just to go along with me, right? You guys trust me, right? I'm not going to waste your time. Have faith, Anyway, so notice that if this mu function is carefully chosen to satisfy this property, that the derivative of mu is actually equal to negative 2 times mu. So the derivative of mu is basically itself. You just pick up a negative on it. Then this would be true. If you were to take the derivative of mu times y, well, mu times y is a product, right? So to take the derivative, you would have to use the product rule. And notice, you would leave the first function alone, excuse me, times the derivative of the second, plus the derivative of the first times the second left alone. That's just the product rule, right? That middle equality there. And then notice, well, if this is true here, if the derivative of mu is negative 2 mu, I can just put a replacement in there like this. Just replace my mu prime with negative 2 mu. Okay, so all I'm saying is if the derivative of mu happens to equal negative 2 times itself, then when you take the derivative of mu times y, what do you get? You get the left-hand side of this differential equation, right? So in other words, if you choose mu carefully, then actually this left-hand side of the dE will be the derivative of a product. So we'll use that later, but for now just accept this, right? So just notice the product rule gives us this, if indeed mu is chosen to satisfy this condition here. Okay, so let's find a function mu that satisfies that condition. Well, if you think about it, as we did on the first day of class, you can just talk your way into it. A function whose derivative is basically itself is going to be exponential. And then if you want a negative 2 to pop out after you've taken the derivative, you need a negative 2 up top in the exponent. So e to the negative 2t fits the bill. So if you make the substitution, if you let mu be e to the negative 2t, then if you look at the previous slide, all I've done here is replace mu's with e to the negative 2t. This line here, I just distribute on the right-hand side. And then this line here, I just point out what I've already pointed out, which is that this left-hand side is actually just a derivative. The derivative of mu times y equals that left-hand side. That's what we said back here. Right, this left-hand side, right here it is, left-hand side equals the derivative of mu times y. Okay, so this is just sort of a big thought experiment, right? So for now, just make sure you can follow the individual steps. We'll talk about at the end here sort of the big picture, how this is used for all such differential equations, not just this example. Okay. The nice thing about having a derivative on the left-hand side, I guess I should say, is that we know how to get rid of derivatives. If you want to undo a derivative, all you have to do is integrate. So that's what I'm going to do. I'm going to integrate both sides. This integral with this derivative just cancel each other out, right? That's how they work. On the right-hand side, you actually have to do some integration, but you can do that if you want to. So notice on the left-hand side, the integral and the derivative just cancel out, and you're left with just e to the negative 2ty. On the right-hand side, you have to do this integration. So integrating this term here is pretty straightforward, right? I expect all of you can do that. Integrating this term here requires integration by parts, which I don't particularly care if you can do. So if you come across an integral involving integration by parts, I would just go to Wolfram Alpha or whatever, Symbolab, your favorite computer algebra system. Symbolab told me that the integral of this negative t e to the negative 2t was this stuff here. So I just grabbed that straight from the computer. If you enjoy doing integration by parts, you are certainly free to do that. And then this is all indefinite, so a plus c. So in the end, right, what were we trying to do anyway to solve the differential equation? We're trying to eventually write y equals stuff. We want the functions y that satisfy the dE. So in the end here, you can just divide by e to the negative 2t. So e to the negative 2t cancels there. E to the negative 2t cancels there. And then c, divided by e to the negative 2t is the same thing as multiplying by e to the 2t. So in sum, what did we do? Okay, we multiplied both sides of an equation by some unknown function mu. We then noticed that if mu satisfies this property here, then this left-hand side of the equation is just the derivative of a product. So then we can unwind that product, right? Just do the product rule in reverse, basically, right? Undo the result of a product, and then integrate our way out of there. And after we've integrated, the derivatives are gone, right? This equation here, there's no derivative. It's not a differential equation anymore. It's an equation where we can isolate the y, and then we are done. That is how this method works in general. So any such first-order linear differential equation can be solved like this. Okay, so before moving on, I should say, why are these things called first-order linear differential equations? So what differentiates them from other differential equations? First order means only a first derivative. So you can certainly imagine differential equations with, say, second derivatives, third derivatives, and so on. So first order means there's no second derivatives. There's no acceleration, if you like. Linear just means that the derivative of y and y itself are linear terms, okay? They are not squared. They are not under a square root, nothing like that. just a dy dt, not inside of a sine or something, and just a y. The y is not squared. The y is not inside a sine. The independent variable stuff can do whatever it feels like. Okay, so g of t could be log of sine of t or something, whatever. So, but to be first order linear, linear being the key adjective, the y and the dy dt are not messed with. Okay, so before moving on, to show you another example, let me just point out any equation of this form can be solved using this technique. The function mu is called the integrating factor. So that's why this method is, the methodology is called solving by integrating factors. And in this previous example, we just sort of thought about what it should be, right? We just said, well, if mu prime equals negative 2 mu, I get this thing that I want. In general, though, you don't want to think about that. There is just a general formula for a mu that will work. You can see the book if you want to see a justification of this. But mu of t is always e, take the antiderivative of p of t, where p of t is this coefficient on y. And then, when you do the indefinite integration up here, this isn't an exponent, it's e to that. You can just ignore the constant of integration. Okay, so I'm going to show you one more example where we don't do the thought experiment. We just basically grab this formula and use it. Before doing that, though, let me just reinforce that you can look at these things with slope fields. So this differential equation here, wherever it is, this guy, y prime minus 2y equals 4 minus t, this is a slope field of that guy. So you can get a feel for what the solutions are doing. So it looks like, if I move this around a little bit, it looks like they are growing off to infinity sometimes, depending on where they start. So if, for example, y of 0 is 0.4 or something, you're going to follow these lines up. Some of the solutions, though, are dying down. Right? They're going down to negative infinity. And there's some sort of like dividing line that separates those two types of solutions. So let's think about that, why that would be the case. Let me look at the solutions themselves here. Where are they? Okay, y equals here. Okay, so notice, right? Any function like this is a solution. So as c varies, right? If c is 1, you get a graph. If c is 2, you get another graph, and so on. If c is 0, notice that term there disappears, and you just get a line, right? Just this negative 2 plus a quarter, 2t plus 1. If c is 1, though, what do you have? You have a line plus an exponential that's going off to infinity. If c is negative 1, what do you have? You have a line plus an exponential that's dying down to negative infinity. So negative c values will drive these functions down, and positive ones will drive them up. And when c is 0, you get a line. So let me just show you what happens when c is 0. Let me turn it on here. When c is 0, you get that line, right? Notice it's cutting along the arrows here. It follows the arrows exactly. That's the c equals 0 solution. Here's a solution when c is positive. It goes up like that. A little hard to see, but there it goes, right? Up and up and up. Zoom out. When c is negative, you get a solution like this. So it's a negative exponential dying down. Okay, so again, the slope field, if you just look at it, it can tell you things like that, right? We expect to have basically two types of solutions. Solutions going to positive infinity, solutions going to negative infinity, and quickly, right? These arrows are going up really quickly, and they're separated by some sort of line, right? There's some sort of boundary that separates them. So we actually could see that from the slope field, and then the solutions themselves correspond to that. Okay, so now let me go to a handout that I would have handed you in class, and let me just talk you through one more example. Okay, so this handout that's on Moodle that I would have given you in class, it lays out some of the methodology I described out loud. So I'm not going to read all this. However, there's one note I should make that I implicitly made in the slides, but should make explicit now. If you want to do this thing with the mu, the differential equation must be written like this. If it's not written like that, and you try to use this methodology, you will fail. You will make mistakes. So the first thing you do when you see something like this is that you must have a coefficient of 1 on the dy dt. Otherwise, this methodology doesn't work. Okay, so here's just a fresh first-order linear differential equation here. Notice this guy here is first order because there's just a y prime. There's no y double prime, no y triple prime. It's linear because the y prime and the y are just as they are. They are not squared, they're not inside of a sign, whatever. Okay, so let's solve this differential equation here. And I put an initial condition on here, but as we talked about last time, you don't care about that till the end. So we're going to solve this differential equation here and then worry about this condition later. Okay, so first thing to note is that this differential equation here, zoom in on it a little bit, doesn't match the form above. Okay, the form above, right, says dy dt has to have a coefficient of 1. So the first thing you got to do is divide by this t, and you get this differential equation. That's what you're actually going to solve. Now, if you want to find the integrating factor mu, this function you're going to slap on both sides of the equation, you can just use the formula from the slide, e to the integral of p, where p again is the coefficient of y. So this is 2 over t right here, guy. So again, if you haven't put the original differential equation in the correct form, then your p of t will be different, and therefore your integrating factor will be different, and things will explode on you, okay? So anyway, I have e to the integral of 2 over t. What's the integral of 2 over t? It's 2 times natural log of t. Ordinarily, you would put absolute values on the t here, but notice it says up front, we're only thinking about positive times, so I can ignore the absolute values. The 2 can be moved inside the log via the exponent rule of logarithms. The e and the ln cancel out. So mu, it turns out, is just t squared. Okay, e to the integral 2 over t dt turns out to be just t squared. So on an exam or on your homework or something, right, this is what you would do first. You can just use this mu formula from the slides. That first example I showed you, I was trying to think out loud about what you would do, you know. When you're actually working these problems, you're not doing a thought experiment about how you would solve such things. You know, you have the solution technique in your pocket, so you don't need to reproduce how you would think about mu. You can just grab the formula from the slides. Now, once we have our mu, we multiply both sides of the dE by that mu. So I put a t squared everywhere. So there's a t squared in the y prime, 4t becomes 4t cubed, and so on, right? And again, the whole reason we were doing this is so that this left-hand side now is the end result of a product rule. That left-hand side is the end result of a product rule having been taken here. So the derivative of t squared y, the derivative of mu y, is this. You can confirm this, right? That this is why we chose mu the way we did, so that this left-hand side is the derivative of a product. And again, you can check, right? Derivative of t squared y, what is that? T squared y prime plus 2ty, right? That's what the product rule says. So this differential equation becomes this. Then we can integrate our way out of there. So if you integrate both sides, the integral cancels with the derivative, as it did in the previous example. So on the left-hand side, you will always just end up with a mu y here, because the integral cancels with the derivative. On the right-hand side, you have to do the integration. In this case, you should not be going to Wolfram Alpha to do this, right? Everybody can handle this. T to the fourth plus c. So therefore, y is equal to, you got to finish by isolating y, divide by t squared plus a constant over t squared. So here are all the solutions of the differential equation. So once you get used to this technique, it's not so bad, you know. There's not a ton of work here, you'll notice, right? So it just takes a couple of times trying this to get used to this technique, to create the end result of a product rule, to then realize you have the derivative of a product, then undo that derivative, right? Those are always the steps. In this particular case, we have an initial value problem. That's what IVP stands for, initial value problem. So recall from last time, that just means I've given the problem an initial value. I've given you a point that the solution must go through. Okay, so at the end here, you want to nail down a particular constant value, as we've discussed before. So what do we know here? That when t is 2, y must be 5. So if I substitute in a 2 for t and a 5 for y, I get this equation here, and we learn that c is 4. Therefore, our final solution is this. There's no c value. It has been nailed down at 4. Okay, so hopefully the two examples I showed you were clear. Again, on an exam or on your homework, this chunk of work here, without the English, unless you want to write the English, this is the work you show. Right? So it's not that bad once you try it a couple of times. As I said in my email, there is another document on Moodle under the daily problems from class section. Those are some practice problems I would have given you and discussed with you in class if we had met. So if I were you, I'd check those out also, and then check out the homework schedule on Moodle. Please let me know if you have any questions when we come back to class on whatever day it is we come back.